Welcome, students. This is an introductory lesson on energy, and specifically the forms of energy that we're going to focus on in physics, or at least in a first-year physics course, and how we express how much energy things have. All right, so we're going to focus on a group of kinds of energy. I don't know about that grammar, but there are lots of different forms of energy. There are, well, let's see, you've probably heard of lots of them, like you'll say like heat. Yeah, okay, we'll call that probably thermal energy. Light, yep, that's energy. Sound is energy. You've probably heard of maybe kinetic energy. That's actually one of the ones that we're going to focus on today. There is a group of energies that are referred to as mechanical energies. All right, so lots of different forms. There's nuclear energy, and I don't necessarily mean like, yeah, there's nuclear power. Okay, that's different. Um, nuclear power generation is about converting energy stored in nuclei into thermal energy, and then into energy of motion, and then into electrical energy that you can then convert into, say, like light or heat or sound energy. So then this eventually will lead us into discussions of energy transformations. But for now, we're going to focus on some kinds of energies that are in this group called mechanical energy. All right, so let's consider a point particle. And when we say a point particle, what we're doing is let's neglect any what's called internal structure that an object might have. All right, so objects are made of things, right? Typical objects. You take a ball. The ball is made of atoms, and those atoms have parts, and the parts of the ball might have different kinds of energies, but let's forget about that. Let's take a very simplified look at things and forget about the stuff that things are made of and just say, a ball is a thing, end of story, right? So we have to forget about the size of things, the shape of things. We just consider them for now as what we call point particles, right? Well, a point particle can have energy. Right? A single object can have energy, and actually only one kind of energy. Right? And that kind of energy it has, well, it can have if and only if the object moves. All right, and so by definition, we call kinetic energy energy associated with an object's motion, or perhaps energy of motion. Okay, so now going a little more detail into this point particle thing, right? If we consider the structure of an object, of the ball is made of stuff, right? The ball is made of atoms. The atoms themselves can move, right? And that's the nature of temperature, right? You might have heard from chemistry that temperature is a measure of the average kinetic energy of the particles in a substance, right? So, if we make the ball warmer or colder, well, then there's energies associated with things that make up the object. We don't want to deal with all that, all right? We want to deal with simple. The thing moves, the thing has kinetic energy. Forget about parts of the thing. The thing has no parts for now. The object is itself as the simplest thing we can think of. All right, forget about stuff it's made of. All right, so a single object can have energy, and only one kind of energy. That's important, right? If we forget about the parts and only think about the thing itself, all that can happen is, well, maybe the thing's moving. Okay, if it is, it has kinetic energy. So which objects have kinetic energy, or how much kinetic energy do objects have? Well, that depends. All right, more mass or more massive objects tend to have more. Well, K. We'll use as a college board, AP physics type students, we will abbreviate kinetic energy simply as K. Some people do it as KE. Right? We'll just use K. The more massive objects, the more massive objects are, the more kinetic energies they tend to have. It's not necessarily true, but more or let's see, the faster objects move, the more kinetic energy they tend to have. All right, those are the two factors that tell us how much kinetic energy an object has. All right, mass and speed. Well, guess what? You know, objects that have small mass but are moving really fast might have the same kinetic energy as a very massive object that's moving slowly. All right, so there's a mix that we'll talk about. Well, how about right now? We're going to define a couple of things. We're going to write an expression for kinetic energy. And, well, let's see. It goes as simple as this. How simple do I make this? Well, how about this? If we look at K as a function of M, so for at a single slash constant velocity, the more the more mass an object has, M, 2M, 3M, the more kinetic energy it has. So we get K, 2K, 3K. That's not great scaling, sure, but this says that kinetic energy is proportional to an object's mass. All right, and here, when we look at speed, well, wait, didn't you just say velocity? Okay, well, here's a big thing about kinetic energy. It's not a vector. There's no such thing as kinetic energy to the right as opposed to kinetic energy to the left. There is no difference. Regardless of what direction objects move, well, they can have the same kinetic energy. All right, so energy has nothing to do with what direction things occur in. And this one doesn't do the linear. All right, so this is for a single slash constant mass. Here's what happens. We go from V to 2V to 3V. Well, if there was some kinetic energy associated with a certain speed, if you double the speed, you don't double the K. What you do is 1, there's 2, here's 3, here's 4. You go 4 times as much. And if you triple, go from V to 3V, the speed, you don't triple kinetic energy, you multiply it by 9. And so that point is the 4, 8, 9. That point's up here. Oh boy. So this curve, and we do have 0, 0 on there because if an object is not moving, it has no kinetic energy. So this looks like that. And this kind of relationship, whoops, is called K is not proportional to V. It's proportional to V squared, right? Here's what we did. We doubled an object's velocity. We double squared its kinetic energy. Some of you will call this, oh, it's exponential. I don't like that word personally. To me, that means a different type of relationship. Yes, I understand 2 is an exponent. This is called a quadratic relationship, referring to that the exponent is specifically a 2. So you will no longer in my class say the word exponential. You will say quadratic. Okay? So, well, that means 2 things we can capture in our expression for K. 1 is that it's proportional to M. 2 is that it's proportional to V squared. Well, there's a 1/2 in the front. That's a harder sell as to why that's there, but you're going to have to take my word for it. Okay? Maybe this is definition 1. I'm not quite sure what these definitions are supposed to be, but I'm going to do this, and we're just going to define, we're going to define kinetic energy as 1/2 mv squared. I'm also going to say, okay, so if K is 1/2 mv squared, let's look at the units of K, ungroup, ditch the box, delete. Now, the units of K must be the following. Let's look at this here. Well, for me, square brackets mean units. So mass measured in kilograms for us, velocity measured in meters per second, but it's velocity squared. So the standard units of, the fundamental units of energy, of kinetic energy, are kilogram meters squared per second squared. Some of you will recognize that that's like writing a kilogram meter per second squared times another meter, right? There's meter squared. Some of you will recognize, oh, isn't that a Newton? The kilogram meter per second squared? It sure is. Sometimes energies are measured in Newton meters. You'll see them expressed that way. We call that a joule. I think all that stuff is probably in this definition. So a joule is a Newton times a meter is fundamentally a kilogram meter squared per second squared. Okay? So we abbreviate joules as capital J's. It's okay? It's okay. Onward. Now, a couple of examples. What's the kinetic energy of this car? K is 1/2 mv squared, substituting 1/2 of 1200 kilograms times 7.5 meters per second. Don't forget to square that number. And what do you get? You get a beefy 33,750, that's a 5 joules. How fast is an object moving if that's its kinetic energy? Well, that allows us to work a little algebra. We're looking to solve for the how fast. The v, let's see, 2k divided by m. That would be v squared. There's an expression for v. I guess I should substitute. Good practice. 2 times 350 joules over 8 kilograms. What do you get? You get the square root of 700 divided by 8, of course. And this object is moving at 9.4 meters per second. Fine? Fine. Here's a nice little ranking exercise. So please do, my students, do, for when I see you next, rank the kinetic energy and explain. Okay? There are provided masses and speeds in terms of m's and v's. So rank. What just happened? I don't know. So let's see. Okay, now. So we have a single object. A single object can only have one kind of energy. That kind is kinetic energy. Okay. What if we had two objects? What if we had what we call a two-particle system? Let's refer to them as mass 1 and mass 2, M1, M2. Well, here's the thing. If you take a single object, any single object, right? It can have kinetic energy, sure, but any and every single object, and by I mean object, I say a mass. Every mass does something to the space around it, right? And depending on where you are in physics, this is either brand new or not, but for my dudes, it's brand new. Every single object, if it has mass, the nature of mass is to create, one of the natures of mass is to create what's called a gravitational field in the space around it. Mass, by its nature, is a couple of things. Mass is, what I say is, that which creates a gravitational field, and that which is affected by a gravitational field. Also, mass is that which, the stuff that resists changes in motion, like resists change in momentum or resists change in velocity. All right, the more massive objects are, the more resistance they have to a change in velocity. The more massive objects are, the greater the gravitational field they create in the space around them. All right, we have a variable for gravitational field. We call it G. And here's the deal. If you put mass 2 in mass 1's gravitational field, here's what happens. Here's mass 1. Here's mass 2. Well, what these things do, what mass 1 does, or mass 1's field, is it exerts a gravitational force on mass 2. This I'm going to call the gravitational force exerted on 2 by 1. Really, on mass 2 by mass 1's gravitational field. Well, guess what? Mass 2 also creates a gravitational field. And what does that field do? Well, that field exerts a gravitational force on mass 1. I'm going to draw that like this. I'm going to say here's the gravitational force exerted on mass 1 by mass 2. And you have heard this before, my people, but regardless of anything, those two forces are the same size. They are what we call equal and opposite. That is Newton's third law. Okay, so who cares how strong or how much mass each one of those objects have? They exert forces on each other. By their nature, those forces must be equal and opposite. All right, so what could happen, right? Well, what does happen is these objects exert forces on each other. What could happen is, I'll say, quote, maybe objects move, right? We're exerting forces on them. So maybe is actually not a good. If this is the situation and we only have these forces exerted on objects, the objects move. Now, move isn't the best word, but for now it'll do just fine. All right, now move, look at this. Look at this. Move means, oh, wait, that means that they could, the system or parts of the system could then have kinetic energy, right? That's energy of motion. So because these things are where they are, placing them there and then, say, letting them go, they could start moving. That means that, well, the system has what we call gravitational potential energy. Potential energy. And I call that, I mean, a lot of people will say, what's potential energy? They'll say, oh, it's stored energy. Well, what do you mean stored? Well, I call this energy associated with objects' position relative to each other. So I call gravitational potential energy energy of position. And there are ways to change the amount of energy that this two-particle system has. And what it has to do with is, well, what are their positions relative to each other? And, well, how strong is this field that each one of them is? And really what that gets down to is how big are these forces that each one of them exert on each other? Okay, now we can talk about if you put things like quite literally like out in space, like in, you know, space, outer space, and we had a couple of planets or a planet moon system. The expressions for gravitational potential energy associated with those things get a little bit complicated. but we're going to focus for a good while, skip that, on a certain specific expression for, now this, what I didn't do back here, is when we say gravitational potential energy, the potential energies for us go U for of course, so U for potential energy, G for gravitational. Some people will say gravitational potential energy or potential energy. We in College Board / AP say UG. Okay, so we want to write an expression for how much gravitational potential energy a two-mass system has. What we're going to do is we're going to set a couple of conditions. One of which is that one of the masses, one of the objects in our two-mass system is the Earth, and the other is just some thing turning our M1, M2 system into an Earth, what we'll call it there's an Earth mass system. All right, so we're going to talk about how much energy does, this ball that we talked about before, the ball have when it's a system with the Earth. So the Earth ball system has a certain amount of gravitational potential energy. Okay, condition 2 is let's talk about near Earth's surface. And the reason we do that is, we're going to talk about the balls here in the room, right? So let's talk about things that happen in the room around us. Near Earth's surface, that gives us a nice bit of leeway. Earth's pretty darn big. So, Earth's radius is 6 million plus meters. So if we go a couple hundred meters higher up above Earth, that's not that far from Earth's surface relative to the size of the Earth. So the nice thing about saying that is near Earth's surface, G, which is Earth's gravitational field, is really fairly constant. The way gravitational fields work, sidebar, is here's a planet. We're really far away from we're far enough away to say that like here and here are very different locations relative to the size of the planet, right? Well, here, gravitational field is a lot stronger than it is here. Okay, when we zoom all the way in to way in there, and forget about the curviness even of the Earth or that planet, the field in that little red box is very constant. Okay, and for us, G, Earth, surface, has this general strength. Not general, but approximate, I should say. It's about ungroup. Sorry. It's about that strong. Stop it. There we go. It's about that strong. And we'll talk more about what that means, what this means really. All right. It's apparently gravitational field strength is a measure of the force exerted per unit mass that's placed in the field. All right. So near Earth's surface, for every kilogram of mass that you put in the field, a force of roughly 10 newtons is exerted on it by Earth's gravitational field. So guess what? You take a 2 kilogram object, well, there's 20 newtons of force on it. You take a 6 kilogram object, well, there's 60 newtons of force exerted on it. Okay? So if we take these two, what do you call them, conditions, there's a little oddity here that, you can read. It's more of a disclaimer. We actually have to be able to talk about differences in gravitational potential energies from one place to another, or one configuration of a system to another, but don't worry about that so much. So here's what we got. All right. Here's the Earth. Here's an object. All right. And here's what we call our arbitrary, let's say right here, we define this system to have 0 gravitational potential energy. We can do that if we so choose. That's a great thing about gravitational potential energies. You can choose whatever configuration you want for a system, for the Earth object system to have zero gravitational potential energy, or someone will define it for you. How do we give this object more, or how do we give this Earth object system more gravitational potential energy? Well, we could do this. We could take the object, come here, take the object and do this. This system, the Earth object system, now has more UG. Or we'd say from here to here, there was a positive change in gravitational potential energy of the Earth mass system. We take the object, guess what? And we move it down yonder. Oh boy, come here. Yep, we move it downward down here. There's now, in this configuration, less gravitational potential energy of the Earth object system. Or we would say that this is a negative change in UG. I guess this is how. So 1 is change. Well, location isn't a good enough word. What we really have to change, how about this? Change separation of the Earth and object. And really what we're talking about there is change height. It has to be height if we're going to change separation. All right, 2, and this is like before, is, well, you can't change an object's mass, but hopefully it follows from a kinetic energy model that more m, and I'll say object, equals more UG. The more massive our object is, the more energy it has as a system with the Earth. Okay? And so we got basically 2 things. Well, sort of 3. 1 is this. How high is something up above, well, not above Earth's surface, but above or below some place that we decide to call an orientation where the system has no energy. All right, that's 1 thing. 2 is how massive is the object. And the 3rd thing that affects how much gravitational potential energy a system has, so watch, I'm going to start. We got UG, we got M, we got H, and we get this. All right, because the whole reason that gravitational potential energy exists at all is because something creates a gravitational field that something else is in. And what we're always going to do is we're always going to use the field that Earth creates and m of the object that we place in Earth's field. And then this height, h, is relative to some defined, quote, height equals 0. Someone's got to tell you from where you measure height, right? You can't just say, hey, how high is that thing? Well, relative to what? The Earth's surface? Relative to the floor I'm standing on? Relative to the top of my head? Where? Okay, so this is our expression for gravitational potential energy. And look what it's measured in. Well, the M, right? We say U, mgh, M in kilograms. G, we said in newtons per kilogram. H in meters. Look what we're left with. Kilograms, Newton meters. Oh, look, it's a joule. Well, of course it is. It's a kind of energy, just like kinetic energy. They have to be measured. They have to be measured in the same units. Okay. Okay. Now, here's an example. A block is lifted above the floor. So I guess so the ceiling we're saying is, now let's call this height 0. This is height 2.2 meters. The block is here, 1.6 meters above the floor. This is 1.6 meters. I'm going to change this. Whoops. Watch. I'm just going to label dimensions. This is 2.2 meters. This is 1.6 meters. Question A says, or A, how about this? A. Question A says, what's that block's gravitational potential energy relative to the floor? Okay, so UG is mgh. UG is 25 kilograms times 10 newtons per kilogram times h. So how high is this thing? Well, how high is it relative to the floor? Well, 1.6 meters. So we get 250 times 1.6. Go, go, go. 400. 400 joules. Is that true? Probably. Yeah. Now, what is the systems? This is actually a crap question. The blocks UG, that's not a good question. All right. Calculate the, this should say Earth block systems gravitational potential energy. The block can't have gravitational potential energy. Single objects can't have gravitational potential energy. Only two object systems can. Okay, so relative to the ceiling, look at this. If we say UG is mgh, UG is 25 kilograms, 10 newtons per kilogram. The height relative to the ceiling is, well, it's 0.6 meters below the ceiling. That is a negative, oh gosh, negative 0.6 meters. Okay, sure. Oh boy, gosh. There we go, it's fine. Negative 0.6 meters. So this system's gravitational, well, the system's gravitational potential energy relative to the ceiling is negative 150 joules. Okay, so a question will either always define for you where to measure gravitational potential energy relative to, or if it doesn't, you get to choose. Okay? Okay, that's a good little intro. Those are two. Kinetic energy and gravitational potential energy are both forms of kinds of mechanical energy. All right, that's where our focus is going to lie in our introductory look at energy. Okay, see you soon.